I will present. This is Tongnyeol Rhee from South Korea. I worked in the Korean Institute of Fusion Energy. Today, I will present my recent result about the CUDA acceleration of the simulation code for Tokamak fast ions. This work carried with my colleagues from Korea Institute of Fusion Energy and UNIST and KIST. From Korea Fusion Energy Institute, these two colleagues provide me the interpolation routine in the GPU, and from UNIST, Dr. Professor Yoon Ui-sung, we collaborate to interpret the C language to the CUDA language. From KIST, Dr. Oh Kyung Kwon, he optimized my CUDA code to more faster code. Let me start. At first, this slide shows a brief introduction of my presentations. Uh, as you can see, uh, I think all of you know carbon dioxide emission-free energy source is very important future issues because we should prevent temperature increase. So we need carbon dioxide emission-free energies. One of the candidate is fusions. Here is a fusion energy scheme. Fusion energy is obtained from this fusion process. Here is deuterium ions and here is tritium ions. And these two ions are fusions and it produces helium ions and neutrium, and it also produces energy, and by using these energies we can produce the power plant, electric power plant. And as you can see, there is a strong Coulomb repulsive force between the deuterium ions and tritium ions. So to overcome this repulsive force, we need very uh, strong energy particles, and the energy is corresponding to the very high temperature. This one is 100 times to, this one is 100 million degrees. This is very hot temperature. So this ions of hot temperature is confined in the magnetic field like structures, and this one is called Tokamak, and this Tokamak confine the hot plasma by using magnetic field. These toroidal coils generate the magnetic field, toroidal magnetic field, and this toroidal magnetic field, ions and electrons are confined like this. And here the fusion process is generate the electric power. And to heating up to this 100 million degrees, we need a heating device, and one of the heating device is neutral beam injection heatings. Neutral beam injection heating is accelerate the ions, deuterium ions, to the 100 kilo electron volt to 1 mega electron volt, and here the ions are neutralized by charge exchange process between the neutral deuteriums, and these accelerated particles penetrate to the strong magnetic field to the plasma, and in the plasma the energetic particles are ionized, and these ionized particles follow the magnetic field, and during OB following process there happens heatings and torque and the current drives. Here, my code NUVDEC simulate this OB following process and heating and torque and current drive calculations. So basic things, what simulation code does are these things. The code follows the orbits in the magnetic field, and these are tiles, and this red dot shows a cartoon of plasma particles, and the my code the code follows the particles orbit like this in the background magnetic field, and during will be following the code calculate the key plasma operation parameters like heatings and torque and current drives. So this simulation result have to be used for real-time Tokamak operations. And this operations timescale is in milliseconds. So we need very faster simulation result, or we can use machine learning. So we need much of data set to teach the machine learning. So anyway, we need to very faster simulation code. So to simulate faster procedure, we uh, are using GPU machines. Before introduce the CUDA code, that means acceleration, I should introduce the NUVDE code on the CPU. This one is shows the flow chart of NUVDE code on the CPU machines. This CPU machines algorithm is particle by particle. At first step, uh, get uh, we get n ionized particles, and we follows after obtain all n particles informations. At first, we select ice particles, and for this for only this particle, we calculate the time evolution function, and this time evolution function is composed of space and time, and this one is magnetic flux. By using this magnetic field flux, we can obtain this magnetic field, and we use the time evolution equation as drift equations. Because the Lorentz equation need much more time, we use drift equations, but this drift equation require derivative of magnetic field. So we need polarized flux and its derivative and its second derivatives. During this calculation of polarized flux, we need bicubic spline interpolation functions. And by using this time evolution function, we time evolve the particles by using first order Runge-Kutta method. So this first order Runge-Kutta method is very easy to implement to the CUDA and CPU. So this one is flow chart, and at first calculate the evolution function and move next time, and we check this particle is inside the wall or not. So if the particle is outside of wall, then we move to next particle. But if the particle is inside the wall, then we check the time, and if the particle is shorter than the time limit, then we repeat this procedure. And after run all particles, then we put out the data to the files, and then we end the code run. And next page, it shows the strategy of accelerations on the device. So our strategy is only on device. So we synchronize time evolution for all particles. That means single instruction and multi data. So, and the other one is we minimize the data communication between host and device. That host means CPU and device is GPU. So it takes very much long time in the code. So we minimize the data communications, and we recycle the device memory, and we use the in-house interpolation code because we use double precision interpolation, so we couldn't find the interpolation code like a library. So we use CUDA interpreted uh, interpolation function, and we also use first order Runge-Kutta time evolutions. We use CUDA tool, not OpenACC, because NUVDEC is very complicatedly interconnected code between functions. So OpenACC is not easy to use in our code. So we plan interpret all the functions to the global function and device functions. So we can run on the device, and this one means key functions called in the main routines is all global function, and global function called the device functions. So this one is our algorithm on the CUDA on the GPU machine. So at first time we obtain we get the n particles information on CPU. So and all the information of particles on the CPU move to the GPUs, and on the GPUs, all particles time evolution function obtained by using interpolation and some calculations, and we evolve times delta t for all particles, and we check all particles. This particle hit the wall or not. That means that this particle is inside of device or not. And we removing a lost particle. That means if the particles are outside of device, then we remove the particle, remove the procedures in the device calculation, and we check time limit, and we repeat this time evolution procedure. And after all time evolution, we copy all information to the CPU, and in the CPU we print out the all information, and by using file we check the how much particles are hit the walls, or how much heating procedure happens in the calculations. So this procedure is implemented in these global functions. These global functions are composed of these simple linear algebra, and this one is interpolations, and this one is also this one is a function to calculate the time evolution function, and this one is a linear algebra also, then this one is time evolution. So these all of procedures are implemented as a global function, and at these global functions there are many device functions. This one is memory access schemes. You can see there are many blocks, block 1 and block 2, and there are many threads, 1, 2, 3, 4, and the particle information is ordered on the memory. So first particle and second particle and third particle, fourth particles, and so on. And but the information of interpolation for uh, interpolation to calculate magnetic field and its derivative, this one is not ordered, so this one is randomly accessed. But this one is particle information is ordered access, but the information of information over interpolation is not this one is randomly accessed. So this random access, and it makes a time consuming procedure. So this one is optimization process. As you can see, the most expensive time consuming process is interpolation procedure. It takes a 61%. The other one is a check of this particle is outside or inside the reorder and in or out GPUs. These two consumes 10%. The other one is a linear algebra. So interpolation consumes most time and particle loss checks and second, and we can reduce time by using CUDA-based library. So algebraic functions are replaced by using CU-BLAS, specifically CU-BLAS DAX-pi and CU-BLAS DAX-car. We can accelerate 1.47 times, and particle loss check is minimized. The interpolation information is set read-only memory, not from the global memory. So we can reduce the time, and this one is 1.16, and simple device functions. Very simple functions are replaced by macro and inline functions. We could accelerate 1.57, and higher number of threads with a coalescing memory access could accelerate more 1.85 times. So I show the final result. This one is a benchmark test with CPU version. We compare with 20 cores Intel core, and it takes 192 seconds with 100 kiloparticles, and by using A10 after optimization, it takes 72 seconds. This one is a debugger and test and compiled here, and we use when we use a 100, then before optimization it takes 35 seconds. it is 5 times faster, and after optimization we could 17 second that is 11 times faster than CPUs. This one is particle time consuming elapsed time, and this one x-axis is number of particle and y-axis is elapsed time. As you can see, CPU version is linearly increased with particles, but as you can see, the number of as you increase number of particles, anyway, it increases linearly. And anyway, we obtain, we achieved this 11 times faster than the 20 core CPUs. This one is my summary. So thank you for your listening.